that all functions are from, let's say, positive integers to positive integers. Is that okay? All functions that we consider whenever we talk about asymptotics are functions of some variable n, where n is positive, n greater than or equal to 1. The value of that function will also be greater than or equal to 1 or greater than or equal to 0. It doesn't really matter. So we'll assume that they're all from positive integers to positive integers. Okay. So what do we do here with asymptotics? In asymptotics, we want to compare how two functions grow as n tends to infinity. Okay. So the question here is, how do two functions, I'll denote it as f of n and g of n. Okay. They are functions f and g, but in this course, we will make it less rigorous. We will just denote it as f of n and g of n. Okay, where n is your variable. Okay, so how do two functions f of n and g of n compare as n tends to infinity? Okay, that's the basic question. So let's look at one example. What do I mean by compare? Okay, so let us take f of n equal to n itself and g of n equal to n squared. Okay, now without really thinking too much, which of these two functions will grow faster? Which will go to infinity faster? It should be g of n, because you have this, you have the square term here, right? So squares are supposed to grow faster towards infinity. So we will think that g of n will grow faster, f of n will grow slower. Okay, but how do we see that? We can see that in many ways. So for example, one of the way in which we can see that is by noting. So one of the ways is by noting that n is always less than or equal to n square when n is greater than or equal to 1. So this implies f of n is always less than or equal to g of n for all n, which means g of n will have to grow faster, right? It's always above f. The graph of g is always above f, right? Moreover, further, you cannot have any constant. So there is no constant. So let me write it this way. There is no constant c greater than 0 such that c times n square is less than or equal to n for all n. You see, I cannot bound n below by any small value of n square. I don't mind, it can be as small as, let me write it on the top. It could be 1 by 1 lakh times n square. This is still not less than or equal to n. This is not possible because eventually for some n greater than or equal to something 100 or 1000, this is going to be false. All right. So this inequality is not going to be valid for all n at any point of time, no matter how small this constant you choose. It doesn't matter. So you can never bound n below by n square. Okay. Therefore, g is larger. It's also strictly larger. Even if you allow scaling, even after allowing scaling, g cannot be made smaller than f. Therefore, g is strictly larger. Okay. So note that these constants are important to us because when we look at rate of growth, we only are concerned with the rate of growth of a function up to a constant multiple, because n square and c times n square will grow in roughly the same way. Right? That constant only helps us in bounding inequalities, but otherwise both of these graphs look roughly the same. So when we want to measure growth of function, we will allow multiplication by suitable constants for that function. We'll ignore them, right? And while bounding one function by the other, we will allow multiplication by suitable constants. That is fine. It will not change the rate of growth of those two functions. Therefore, we can multiply. Okay. Right. So G is strictly larger than F in terms of growth because G is always larger than F in absolute terms. And no multiple of G can be made to be less than F. Right? That is the idea. Therefore, G is much, much bigger than F. Is this much clear? This is the intuitive idea. Okay. So another way to look at this, even a
Sir,
strong, yes.
can we say n will be greater than n square for some like for some points? After that, again n square is gonna be less greater
That can
than
happen.
n.
Yeah, that can happen in the above case, no? In the red case that
Yeah.
I've written. That can happen for a few values, but eventually it's going to be larger. Okay, so that's a good point. I was going to write it in the formal definition, but okay, let me point it out here. We don't really need for n. We only need it for n eventually. Like for all n greater than or equal to n naught. That is also enough. Okay, that is also enough. That's not a problem. But when you want to study what happens as n tends to infinity, you understand, right? We want this to be true eventually for all n greater than or equal to some n naught. Okay. So I have not given you the formal definition or anything. I'm just trying to tell you what is the how do you measure growth between two functions. Okay. So this is one way of measuring growth. There is another way of measuring growth, which is in fact stronger. Okay. So I'll just take the fraction. I'll take g of n by f of n. This is n square by n, which is n. And this goes to infinity as n tends to infinity, right? So even if I divide g by f, this goes to infinity. So g is going to infinity much faster than f. On the other hand, if I take the fraction fn by gn, this is n by n square, this is 1 by n, and this goes to 0. So fn is going to infinity much slower than g. That's why fn by gn goes to 0. Sorry, 0. Is that clear? That's You might think that the second way is in fact a neater way to, it's a cleaner way to measure the growth, but it's also a stronger way. So what I wrote down below in point B, that will imply what we were saying in point A. Okay, so point B is stronger, sometimes neater, but many times computing this fraction might not be so easy. That is why point A is also important. All right. Okay, so one would ask whether these limits only go to infinity or zero. Not quite. They could go to a constant. Okay, limit might exist and the limit might be non-zero. But in those cases, the two functions will actually grow roughly the same. Okay, rate of growth will be roughly the same. So we'll see that those cases also. Okay, but this is all about asymptotics that you need to know broadly. Now we'll go to the definitions. So everything is clear up to this point.
Yes.
Okay, I heard two voices. Anybody else? Anything?
Clear.
Okay. Okay, let's continue. So what we are interested here in is what is called big O and little o notations. Once again. Yeah. Big O and little o notation. Yeah. What is that? So f and g are two functions going from z plus to z plus, positive integers to positive integers. I will not keep repeating it. We'll just assume it that way. Okay. So the definition is define f of n is equal to big O. Okay. Make sure that you write this O big enough because there is also a little o. Okay. It should be clear which one is big and which one is small. Right. So make the big O as big as you can when you write it. So we write f of n is big O of g of n if essentially f is bounded above by g. G is larger than f up to constants. Okay, that is the meaning, just as we said. So if there exists a constant c greater than 0 or okay, and n not positive, so positive integer, you know that. So let me just write greater than 0 or okay. And not positive integer. C could be a real number, okay? It could be 1 by square root 2. That is fine. Such that f of n is less than or equal to C times g of n for all n greater than or equal to n naught. Is that okay? So we are just saying that g is larger than f up to a constant multiple. And constant multiples are not important to us when we measure growth of functions. So this says that g grows larger than f. Is that okay? That is the meaning of big O. And you realize why we use this O notation because the constant is not important to us. Therefore, we don't need to know what the constant is. Similarly, we are only interested in growth as n tends to infinity. So this needs to be true beyond a certain point only. For first finitely many values, even if it is not true, not a problem. So we only need to know this for all n greater than or equal to some n naught. Again, what is that n naught? We don't really care. What we care is as n tends to infinity, this is true. So knowing what n naught is also not so important. Okay, so we don't even bother about what the constant is, what n naught is. We'll simply say fn is big O of g of n. That is all we need to know. Okay, so we have compressed everything else and written it down in a form where this is all that we need to know. This is all that is important. Okay. Right. So what is little o? Little o is exactly what I showed you in the other definition. So we define f of n is little o of g of n if it's a second definition. So now what we want to say is f of n, think of little o as saying very, very small, insignificant, or very, very small. All right. So f of n is little o g of n if f of n is very, very small as compared to g of n. Okay. What does that mean? If limit n tending to infinity f of n by g of n is equal to 0. Okay. When will this limit go to 0? When f of n is much, much, much smaller than g of n. It will not be a constant even. It is so small that the limit becomes 0. Is that okay? So that is the meaning of little o of g of n. So f of n is very small as compared to g of n. That is what we say That is how we write f of n is little o of g of n. So much is clear. We have seen both of these in the previous slide. This is the formal definition. All right. So now let me go to another set of definitions, which is uh, sort of a mirror image of these definitions that we have already seen. Okay. So now this is big omega and little omega notation. Okay, big omega and little omega notation. Okay. What does that mean? These are mirror images. We were using big O to say less than or equal to, we'll use big omega to say greater than or equal to. We'll use little o to say that limit goes to infinity, limit goes to 0. We'll use little omega to say that the limit goes to infinity. Okay. So now we define f of n is big omega g of n if exactly the same way up to a constant. So there is a constant c greater than 0 and positive integer n naught, because we want this to be true eventually, such that f of n is greater than or equal to p times g of n for all n greater than or equal to n naught. Okay, again, the constant does not matter, n naught does not matter. F of n is bounded below by g of n up to a constant. Okay, so rate of growth, now the growth of f is larger than the growth of g. That is when we'll say big omega. Is that okay? Further, we define f of n is little omega of g of n if, now when you say little o, f of n is very, very small as compared to g. Now f of n is very, very large as compared to g. Okay, so if f of n by g of n, sorry, the limit n tending to infinity, f of n by g of n is infinity. Okay. Now in calculus, you may not be using the term notation limit is equal to infinity. You will say that it is greater than every positive integer, but we are just misusing notation here. I'll just write equal to infinity, but you know what it means. You know what it means for the limit to be infinity. It is larger than every positive integer eventually, right? So these are the two things. So is this much clear to you? So then immediately what do we get? So you check this, okay? Now this is up to you to check on your own. It's like small homework for you, okay? So what do you have to check? Firstly, f of n is big O g of n if and only if g of n is big omega f of n. And secondly, f of n is little o g of n if and only if g of n is little omega f of n. Okay, you see, these are mirror image notations. Should be clear to you just by the way we defined it, but anyways, try writing it down. All of you know how to write a proof. Okay. Start with left hand side, prove that right hand side is true. Start with the right hand side, show that left hand side is true. Okay, very easy. Is that clear?
Sir, can you explain
Yes.
big omega again?
Big omega? Okay. So same thing. So f of n is big omega of g of n. if just like big O, previous slide, when you wanted big O, there is a constant and n naught says that eventually up to constant we have less than or equal to. Now eventually up to constant we have greater than or equal to.
Sir,
So
that
when we
means
said
after the constant, the sign will change, no?
yes, the inequality sign changes, which means now Fn is greater up to a constant. You can even write this as g of n less than or equal to 1 by c times f of n. But that says g of n is big O f of n. It's the same meaning. That is what we have to check in the remark. Okay. So in the big O case, we wanted to say there was less than or equal to up to multiplication by a positive constant. Big omega, we want to say we have greater than or equal to up to multiplication by a positive constant. Because that multiplication by positive constant is not so important to us, right?
Okay.
We'll see more examples and then it will become clearer. Okay, right. So let's look at some examples of this. Okay, so 1 minute, let me stop sharing because I need to open a PDF for the questions. I'll continue sharing in 1 minute. Okay, let me just pick some questions. Can you see this PDF? So this is some notes from last time where there are some examples. Okay. So yeah, we have already seen these definitions. Look at this example. Okay. See the constant function one is big O n because one is less than or equal to n, right? Similarly, one is big O square root n because one is also less than or equal to square root n. Square root n is big O n because square root n is less than or equal to n all the time for all n greater than or equal to 1. Okay, that's why we are taking positive integers because for something less than 1 square root might be larger, right? We know that, but all the usual easy inequalities are true when the numbers we take are all greater than or equal to 1. So we'll assume that. Okay, so square root n is less than or equal to n for all n greater than 1. So square root n is big O root n. Now is n big O square root n? What do you think? Yeah, so when I ask questions, I don't want you to give me the correct answer, but I want you to give me an answer. So answer quickly. What do you think?
No. N
Yes.
cannot be less than equal to root n.
N cannot be less than or equal to root n. Okay, but eventually up to some scalar multiple, can it be true? I need inequality only up to multiplication by a constant. What if I make the constant so small that this becomes true? So small or so large? So n is not less than or equal to square root n. That's correct. But can n be less than or equal to some 100,000 times square root n? Or 2 raised to 2 raised to 56 times square root n? So that also cannot be true because it's multiplication only by a constant. Okay. So let me explain this line by line. So is n big or square root n? Answer is no. And let's do a proof. Okay, proper proof. So the hint here is n is n raised to 1. Square root n is n raised to half, right? So in the exponent, if the number is smaller, then it cannot be larger. Even after multiplication by whatever constant you want, it cannot be true because the rate of growth has become smaller. Is that intuition clear? Forget the proof. Is that idea clear? In the exponent, if you have smaller numbers, the rate of growth cannot be large. Okay, no matter what you do. So let's prove by contradiction. The proof has to be by contradiction because we are asking, is this equal to big O? You have to say no. So you have to start by thinking, suppose it is, and then get a contradiction, right? So suppose it is big O square root n, which means by definition there is a constant, there is an n naught, such that n is less than or equal to c times square root n for all n greater than or equal to n naught. This was the first line. Okay. So now if I take fractions, what it means is n by square root n is less than or equal to constant for all n greater than or equal to n naught. But then this is square root n by square root n. So square root n is less than or equal to the constant for all n greater than or equal to n naught. This is wrong, right? Because n tends to infinity. So after some point, this number is going to be larger than the constant, right? Here itself, it is clear what it should be. So you can stop writing the proof here itself and say this is a contradiction. But if you want to detail it more, if you want to give more details, then you just point out from what n onwards this inequality is not true. That turns out to be this. You can find out. You can take this n naught plus 1 or you can take c plus 1 whole squared. Anything larger than that, the square root of this number is going to be greater than or equal to c plus 1. Okay, you can just work it out. That is easy. Therefore, this claim is not true. This is a contradiction. And so n cannot be big O square root n. Is that clear? Is that okay? Can't hear somebody was speaking something. Can you speak louder?
We want to note down. Please wait, sir.
Sorry?
Sir, I want to note down. Note down.
No, no need to note down. I'll share all these things with you. Don't waste time in noting down. Okay, I'll share these things with you. Your homework is to make notes. Okay, you have the recording. I'll give you these slides. Go back and then try listening to these in whatever fast forward mode or whatever it is. Quickly review them. Look at the slides. Make your notes. That is your preparation for your course. If you do this much, you will be prepared for all the exams. Okay, so do that afterwards. That is your homework. Okay, don't note it down now. All right. I want you to have pen and paper with your in your hand, but that is for, if I ask, is this true or not? I want you to work out and tell me whether it is true or not. Those kinds of things. but don't note down everything that you see on the screen. Okay, this is for the whole course. Yeah. Okay, so that is what this is. Let's look at some more examples. So this is a contradiction. N is not big O square root n. This is not true. Omega also the same way. So n is omega 1 because now n is greater than or equal to 1. The reverse inequalities. Square root n is also greater than or equal to 1. N is greater than or equal to square root n. So we have all the reverse inequalities. Now is square root n equal to omega n? Omega should be thought of as greater than or equal to. So is square root n greater than or equal to n up to constant multiple? Again, the answer should be no. And again, the proof should be by contradiction. So try writing this on your own. This is your exercise. Okay, this is another homework. All right. So now these are two theorems that I have actually proved there, which is to show that Fn is big O Gn if and only if Gn is big omega Fn and for little omega also. Okay, so these are some slides. I've already explained this to you. And now examples. So one is little o of n. Okay, little o means very, very small. So when I take limit of 1 by n as n tends to infinity, this is 0, so this is true. 1 by square root n limit again goes to 0, so this is also true. Square root n by n is 1 by n. 1 by square root n, again limit is 0, so this is also true. Square root n is little o of n. Now is n little o of square root n? No, because when you take the fraction n by square root n, this is square root n and this goes to infinity, not to 0. So n is not little o square root n. Okay. We already saw that n is not big omega square root n. Sorry, n is not big O square root n. N is in fact also not little o square root n, right? For omega, again, as we saw before, the reverse inequalities. Okay, so n is little omega 1, square root n is little omega 1, n is little omega square root n, but square root n is not little omega n. So these four are exercises for you. Okay, try writing them down. Same kind of proofs. Very, very easy. And then the last remark that I mentioned, Fn is little o Gn, if and only if Gn is little omega Fn. The proof is here. I will share these with you, but I want you to at least try writing them down once without looking, and then you look at this so that you'll learn. Okay, that is what this is. So theta notation is something else. So we'll do the theta and rest of the stuff next time. Okay, so today's class is only about big O, little o, big omega, little omega. That's all. Okay, so this is what it was. Now let me take you through the book and let's look at some more examples. So oh, another thing that I wanted to mention, you might think that this lecture is going faster. It is going faster because this is also being recorded, right? So I am expecting that you will go back and look at the recording once again for things that are not clear. And then when we have some tutorial or discussion session, I'll beforehand declare when we are going to have a discussion or when we are going to have a tutorial. At that point of time, I will expect you to have already looked at all these things and come back to me with doubts and questions. Okay, so these lectures will be faster because these are being recorded, and I will expect you to go back to these to look at things that are not clear and then come back to me with questions. Okay, so this will be slightly different from a classroom lecture because this will be a little bit faster. Okay, so as I already said, a lot of things are homework for you. You have to go back, look at these, make notes. You have to make notes. If you don't make notes, if you don't write these things down and practice by yourself, you will forget. Okay, so that is one important thing. In between, I'll give you these exercises. You will have to do those as well. All right. Yeah, somebody was saying something.
So where is this recording going to be stored?
So I'll put it on YouTube so nobody has to worry about storage space or anything. Okay, I'll put it on YouTube and share a link with you. Is that okay? It will also be on MS Teams, but then MS Team, I don't know how long it will stay. Some last year, some videos eventually got deleted by mistake by somebody or something, so it was a problem. So I'll put it on YouTube so that nobody will delete it, even by mistake. Okay. Yeah. All right. So this was the book, and let's go to this is what we were looking at. Point number 3, growth of functions. Okay. So let's click and go here. You might think that all of this is too much work, but it is not actually. Okay. If you do so much of work every week, then you really will not have much work to do separately for your exams. Okay. So I really want you to work on these things every week so that towards the exam date, you really don't have to prepare too much. Okay. So whatever parts I show you from the book, I will also expect you to read those parts. And that is also one sort of revision. Okay. Right. So this talks about asymptotic notation. It, they talk too much, they give lots and lots of examples, but this is basically what we're looking at. There is a theta notation, which we'll do next time. Where is, yeah, so we have seen big O, little o. They are thinking of it as the class of all functions which are big O g of n, which is essentially the same thing because multiple functions can be big O of the same function at the same time. They are collecting all those functions into a single set. We are not using the set notation. We are just writing Fn as big O gn. Okay. So big O, then we have big omega, right? Then we have this remark, which is Fn is big. Okay, so not this one. Okay, theta we have to see next time. So there's little o notation and then little omega notation. Okay, so much we have seen. Now let's look at some examples. So there are these transitivity properties, but for that I'll also need to cover theta. So theta, let's do it next time. So this is on hold. Let's look at some examples. And yeah, this is good. So example 3.1.4. Okay. So what do you think about this? Is 2 to the n plus 1 big O 2 to the n? Now work it out. Now you have paper and pen in your hand. Now try working it out and give me an answer in 2 minutes. Is 2 to the n plus 1 big O of 2 to the n? It will be right because 2 to the n plus 1 is 2 times 2 to the n. So the constant here is 2 and it is true for all n greater than or equal to 1. Okay. So easily 2 to the n plus 1 is big O 2 to the n is 2 to the 2n big O of 2 to the n. Now that is something you have to check. Okay. In fact, the answer is no. Okay. 2 to the 2n is not big O 2 to the n. And the proof is very similar to something we did before. N square is not big O or n is not big O square root n or n square is not big O n. Same kind of proof. Okay. So those are a few examples. Let's look at some. So whatever examples I show here, I want you to try solving those, but we'll also solve those in the tutorial again. Okay, but I want you to try before the tutorial comes. Is that okay? Yeah. So here, let's look at some simpler cases of what is given here. Forget the k, think of k to be equal to 1 and think of epsilon to be equal to 1 for simple case. Okay. Log n and end. Which way does it go? Is log n big O of n? Is log n little o of n? Is log n big omega of n? Is log n little omega of n? Find out. Okay, try working it out, find out. N and constant. Constant raised to n. Okay. You can think of C as 2. So n and 2 raised to n. Is n big O 2 raised to n, little o 2 raised to n, big omega 2 raised to n, little omega 2 raised to n? What is it? Okay, so these two examples, A and B. You don't have to note it down. If you forget which ones I'm asking you, you can go back to the recording and see which one I'm asking you to solve. Okay, so point A, point B, and then try point D. Okay, 2 raised to n and 2 raised to n by 2. Which way is it? 2 raised to n is big O 2 raised to n by 2, little o 2 raised to n by 2, big omega 2 raised to n by 2, little omega 2 raised to n by 2. Check. Yeah. Similarly, take C equal to 2 and then try point E. N raised to log 2 or 2 raised to log n. How do they compare? Log, you can assume it is some log. Okay, doesn't matter. N raised to log 2 and 2 raised to log n. Big O, little o, big omega, little omega. Check. Okay. If it is true, you only need to give an inequality. If it is false, then you need to give a proof by contradiction. Is that okay? So point number A, B, D, and E. Checking big O, big omega, little omega. That is also homework. Okay. We will solve many of these in the tutorial also, but I'll do that faster. Okay, because I will expect you to have tried it beforehand. Okay, so is that much okay? Everyone, this is what you have to try from the book. Okay, and then there are some examples from the slides also. So slide I'll share with you, book is already there. I'll put this video on YouTube and give you the link. Okay, so today is Wednesday. We will next meet on Friday. Is that okay? We'll next meet on
Okay, sir.
Friday. Before that, I want you to do all these things.
When are you
Okay, so that is all for today, and I'll stop here now. Okay.
sir, when are you going to send the link, sir?
Yeah, I'll send the link in some time. Let me see. Okay. I have to upload it on YouTube, so depending on how much time it takes. Right? So,
Thank you, sir.
okay.
Thank you.
Yeah,
Thank you.
bye. Yeah.